Yeah, so hi, I think we've started now. Yeah, so I think we'll just wait a couple more minutes, like 3 more minutes until everyone connects. In the meantime, of course, if you want to ask something, please feel free. I'll gladly take your questions even before the tutorial starts. I hope you can hear me well, but I'm not sure. Yeah, you can. Let me see if you can. Yeah. Yeah, cool. That's nice. Okay, that's cool. Yeah, thank you, Xavier. Okay, so I think we can get started. Is time now? So first things first, I'll share my screen. Okay, yeah. So here we go. Let me put this presentation mode. All right. So first of all, I'm not entirely familiar with the Airmeet platform. So I guess the preferred way to put question is that you interrupt me freely and speak. So that's more lively discussion. Okay, yeah. So let me check something. Yeah, I think everything is fine. Let me just hide this for a minute. Yeah. So okay, let's get started. My name is Mário Pereira. I'm a researcher at Nova Links, the computer science lab of Nova School of Science and Technology. Here in Portugal. So my affiliation is wrongly shown on the ICFP program. So that's my past affiliation. My current affiliation is Nova Links. I've been working on a tool called Cameleer, which is the focus of this tutorial, of course. So I'm here to present how you can conduct deductive verification of OCaml written code inside Cameleer. So before starting the actual presentation, let me do a couple of announcements. I'll not only me, but also my students will be talking about Cameleer in workshops, namely the ML Family Workshop on the 26th, where I'll be presenting the project and the tool. You can consider it a shortened version of the first part of this tutorial. Okay, and on the next day, I think, OCaml workshop, Carlos Pinto will be talking about our use of Cameleer to formally verify a part of the set module that is shipped inside the OCaml standard library. Okay, so in terms of this tutorial, this first part will be mainly for presenting the tool, the project, and the perspectives. And the second part, I'll be mostly doing examples or live exercises, if you want to call it like that. Okay, so let's begin this discussion by taking a look into nowadays research tools or research on deductive verification for imperative languages. And we can say that it has been fairly successfully applied to imperative language, because we can actually cite a number of different tools, many different verification tools for this kind of programs. For instance, Boogie, Daphne, Very Fast, Framacy, Workhorse, all of these are quite useful to verify imperative programs. But what is somehow surprising is that deductive verification has been seldom applied to the functional world. I mean, to tackle the verification of programs written directly in a functional language, which is surprising, because functional programs should be easier to verify and to get correct in the first place. Let's pick OCaml, for instance, as a representative element of the functional family. For most of times, OCaml features a clear syntax. Okay, it has a well-defined execution model, or in other words, a well-defined operational semantics, and it's a multi-paradigm language, which means that one can easily write concise, efficient, type-safe code. Moreover, OCaml is the language of choice to implement software where correctness and safety are of utmost importance. We could cite a number of tools, like, for instance, the Coq Prophecies and Framacy analyzer, the Very Fast itself, which is written in OCaml, the Astra Static Analyzer, Infer, which is used and developed by Facebook, the Curricle Model Checker, AlterGo SMD Solver, the EasyCrypt tool, which is used to verify cryptographic implementation and algorithms. And outside the academic world, things like the Mirage operative system, which is also developed in OCaml, parts of the Docker Container Manager, parts of the Messenger chat system on Facebook are also developing in OCaml, and more recently the Thesis blockchain, which is entirely developing in OCaml. So it seems like programs written in OCaml, given the features of the language and given its application on sensitive software, so it seems like these kinds of programs are excellent targets for deductive verification. And yet, there is no easy to use deductive verification tool for OCaml written code. Because up to this point, if you want to verify or to get certified OCaml code, you should either write that code base in a proof-aware language and then extract it, for instance, Coq or Y3, which means that, taking this road, you need to rewrite entire code bases for the sake of verification. Or you could go and use an interactive tool, like, for instance, writing your code directly in Coq or in a tool like CFML, which means that you need to write a couple of more proof steps by hand. And in my opinion, this will hardly ever be the choice of any regular programmer. So my first goal is to build, or when I started this project, my first goal was to build a deductive verification tool that OCaml programmers could use. And so, what are the main features that I have identified that I really needed, okay, in order to build such a tool? First and foremost, a specification language for OCaml, because I need to annotate my programs with specification elements, right? So I need a verification condition generator in order to compute verification conditions from an input annotated OCaml program. And now, since I'm targeting, or I have a clear focus towards proof automation, I need to be able to interface with SMT solvers that can discharge these the generated verification conditions. So in a sense, what I wanted was to bring the successful SMT-based verification approach from other tools into the realm of OCaml programming. Okay, so that's how the Cameleer project was born. Cameleer is a 2 years project funded by an individual Marie Curie fellowship, so which means that I've roughly been developing Cameleer about a year now. Yeah, more than a year actually. And so the result so far is the first automated tool for the verification of OCaml programs, or more precisely, programs that are written in OCaml and annotated with a specification language. What's that specification language? Well, it's the recently proposed Gospel, which stands for Generic OCaml Specification Language, and I'll be presenting Gospel in a couple of minutes. And then the second key ingredient up to this point in the project has been a translation from input OCaml programs into the Y3 verification framework. Okay, so I'll give you a little bit more of the details of the translation in also a couple of more slides. In terms of research expectations, from the Gospel or the specification point of view, I want to be able to develop a specification language that OCaml programmers can read. I mean, they can understand the formal specification that I attach to my program, to my OCaml code. But even more importantly, I want them to be able to write gospel elements. In terms of proof, of course, the main idea is to use a proof environment. I want actual proofs, but I want to abstract it as much as possible to the front end OCaml program, if you want to call it like that. Clear focus towards proof automation, because it is my opinion that that's maybe or that will be easily the choice, or more easy the choice of regular programmers if they can do their proofs mostly automatically. And finally, in terms of developing Gospel and features perspectives for Gospel itself, we want to make it, or to keep evolving it into making it a more mature proof language, like adding and missing OCaml nice features such as GADTs or polymorphic variants. I'll talk about that also later in this session. So in this first part of the tutorial, I'll be mainly presenting you the Gospel specification language, and then talking about practical aspects regarding the use of the Cameleer tool for the verification of OCaml programs. I'll show you a couple of examples and focus on the translation from OCaml into the Y3 verification framework. Okay, so let's get started with Gospel. And let's look at what is the life of a regular or every day of an OCaml programmer these days. So imagine that you are using a library which offers you a module, or implementing a queue data structure, a FIFO data structure. And so normally what you'd see in this .ml file would be these 4 lines of OCaml code, right? So in some sense, you see that your data structure is polymorphic, right? And you know there are 3 functions: create, push, and pop. But that's pretty much it that you get only by looking at these 4 lines of code. So if you are lucky enough, you'll have some informal comments or common specification written in natural language, if you want to call it like like that. So okay, it confirms that the type of queues is polymorphic. The new queue is initially empty, which you could guess, but now, okay, you can be almost sure. What is interesting already from these two informal comments is that, okay, the model that this data structure is using is appending new elements at the end of the queue and removing from the first element when you call a pop. Okay, that's nice about the way that the structure is implemented. But for instance, can we call pop on empty queues? And if so, what happens? The program just crashes? You are not supposed to do it at all, or it just simply raises an exception? Because, for instance, I know it cannot return an option value because the return type already says that this is not an option value, but can it raise an exception? So maybe to answer those kind of questions, we need to go a step further and try to apply a richer specification language. So for instance, if I want to implement a queue, or the queue implementation is an imperative one, so maybe I'll need to turn myself into separation logic. So in that case, I'll need to say that my data type or my data structure is equipped with a representation predicate called R, which basically states that this lock, which is the entry pointer in memory to the queue, represents a well-formed queue inside the heap memory, where it has this model, which is a list, and in the sense, a list is more of a mathematical list rather than an OCaml list. Okay, and so this is an heap predicate, so it's also parameterized by the heap memory itself. Okay, so that's still fine. I can still read this line. So now, when we get to create, things start to get a little bit more messy. In some sense, I have a post condition, which is introduced by this ensures clause, right? And now this lambda says that, okay, I'm binding the result of calling create, and I name it Q, and I say that now there is a model, okay, a new L, a new list, which is the empty list, and so I say that I have a well-formed empty queue in my memory. Okay, so now if I turn to push and pop, now it gets really or more difficult to read this kind of separation logic specification. So in some sense, I can still guess that, for instance, for pop, okay, the queue must be well formed, that I could expect, but do I really need to say that every time? Of course, the queue should be well formed inside the memory, and it should not be empty, or in other words, in specification terms, the model should not be empty. But yeah, this is tricky to read, and I'm really skeptical in thinking that a regular OCaml programmer could be writing this kind of specification. So that's how the gospel language enters the scene. In this case, instead of attaching representation predicates to data structures, what I'm doing is that in gospel, every data structure has an implicit representation predicate, and what I can do is that I can attach models fields to my data structure. In this sense, I'm saying that I want to model my data structure using a list. Okay, once again, which I call a view. So in some sense, it's going to be the list of all the elements stored in the queue. And now, once again, now I name my result of create queue, and now I put a post condition that only talks about the view model. And of course, it states that the newly created queue possesses an empty model. So now, when I get to my more problematic functions like push and pop, things, I hope, get a little bit easier for programmers. And for instance, in this sense, push takes an element called view and queue in the specification, because here I call it X, but I can rename that on the specification, no problem. And I'm saying that now this is interesting for a programmer, that now he or she can be sure that the push function is actually performing a side effect on the data structure. Okay, So using these modifies clause, or this modifies clause, says exactly that I'm modifying in memory the Q data structure. In terms of postconditions, everything is once again written in terms of view. And so since I'm attaching a new element to the end of the queue, so what I say is that the previous version, or the version of the value of view on the pre-state of push, is I can access it using the old keyword. That's what it means. Old queue view. It's the value of view on the pre-state before calling push. Okay, and so now on the pop side, now this precondition is pretty obvious. So you are not supposed to call pop on a non-empty, or sorry, on an empty queue. Once again, there is a side effect on the queue. Once again, we have a modifies, and so the value v that is returned, the first element of the queue, right? Not the first element stored in memory, but the first element that was inserted in the queue. So that's what you are returning. Okay, so and that's once again the idea of using this post condition with the old version of view. Okay, so that was a teaser for the use of the gospel specification language. In summary, gospel is an expressive language where user writes specification mostly in first order logic, but you have some nice extensions like recursive definitions, algebraic data types, and the flavor of high order logic, in the sense that you can use high order computation where argument functions are pure. I'll give you a little bit more details in a couple of slides. So it is concise, or it's in some sense it's conciser than separation logic, which is a good improvement when you want to use gospel as a surface specification language. That's a big improvement over separation logic. Very, very important. It is not tied to any particular verification tool. So in some sense, gospel is the same as GML or ACSL is for Java and C, respectively. And in our paper on formal methods 2 years ago, we also presented the formal semantics of gospel using a translation by means of a translation into separation logic. So when you write your function specification in gospel, you can still think about it as a triple written in separation logic. So let me show you a couple of examples of how that works. And of course, more details are presented on this paper. Okay, so yeah, before going into more details about this translation, I just want to stress that a very important aspect of gospel use in practice is that we hope gospel feels natural to OCaml programmers. This is mainly due to the fact that gospel terms are written in a subset of OCaml plus quantifiers, right? Gospel elements are written in these special comments, but they are translated into OCaml, proper OCaml attributes using the PPX-like infrastructure. Once again, we'll see a bunch of examples later on. So for instance, imagine that you have an empty function over the data type T. In this case, you can state that if you have a logical function size over this data type T, after an empty call, of course, the size will be empty and there would be no elements inside the newly created data structure, which I can state using this universal quantification, say that the occurrence, once again, this would be a logical function, the occurrence for every possible element in the domain is 0. Gospel is under active development, and contributions are mainly due by myself, Jean-Christophe Iliatre, Claudio Lourenço, and Clément Pascuto. The link to the GitHub repository is given below. All right, so let's take a tour around gospel features and now focus on the translation part. So still on the idea of the queue data structure, let's imagine that I want to specify a test of emptiness. So I call this the isEmpty function, right? And this empty function returns a boolean, which I call b. And so my post condition is a very simple one. It says that this boolean b is true if and only if the model view is empty. Okay, the empty here empty is just a syntactic sugar for the empty logical list. Now, this is the first such example of translating gospel into separation logic. All right, let's start by the post condition, which says that the boolean b that is returned, of course, it is true if and only if now the logical model L, okay, remember the first specification that I shown you of the Q data structure using separation logic is nil, the empty list. So the square brackets here are just used to represent a predicate that does not depend on the heap, a pure predicate if you want. Now, more interesting, on the precondition, right? I said that in gospel we are implicitly attaching to every argument of a function a representation predicate. So I'm putting this here on the precondition, but I'm also using what is called a read-only permission. And why? Because in this function, the Q argument is for read-only purposes. Okay, so how do I know that? Because there is no modifies clause talking about Q. So in that sense, from the moment where you do not write any modifies clause talking about an argument of the function, that argument is implicitly considered read-only. And that's kind of good because reasoning about read-only arguments is much easier than reasoning about arguments that you can mutate inside the function, of course. Okay, so read-only permissions were introduced by Arthur Charreau and François Potier in their ISOP 2017 paper. Okay, and the idea is that this is an extension to separation logic with new rules and this kind of reasoning on read-only permissions. It is used only, or you can write only read-only permissions in preconditions. They are implicitly returned in post-conditions, so which means that, of course, you can retain access to the Q itself after calling the isEmpty function. You do not lose possession of Q. And read and write permissions can be locally turned into read-only permissions, which in other words, it works with local scopes, or you can use read-only permissions to work with local scopes, and that's also implicitly implemented inside gospel. Or what I mean is that read-only permissions are implicit inside gospel when you say that your argument will not be mutated by the function. So now let's see three different variants of concat functions for our FIFO structure. The first one, what does it do? So it's going to touch both Q1 and Q2. So both elements should be presented in the modifies clause. And so now I'm sure that neither of them is a read-only argument. And so in some sense, I want them to be disjoint in my memory, and that's implicit inside gospel. So that's a design choice of gospel, that every element or every element of an argument is, or all arguments of a function are disjoint from each other inside the heap memory. If you look at the translation into separation logic, there you would need to explicitly state that these are disjoint in memory using their representation predicates. So in terms of post conditions, now what the Inplace Concat function is doing is actually something very similar to the transfer function that you can find in the Q module from the OCaml standard library. So it empties the Q1 Q and attaches every element of the Q1 to the end of the Q2 data structure. Okay, so that's why we are using both old of the Q2 view data value, and also the old value of the view model for Q1. Okay, so that's in some sense that will be the new value for view. All right, so in terms of translation, we've talked about the precondition. Now the post condition says, of course, you regain possession or you do not lose possession of your Q1 and Q2 data structure, but you update the logical models accordingly. So the new model is the empty list for Q1 and the new model for Q2, right? L2 prime is the concatenation of the old models. So yeah, this is a typo. This should be switched. All right. So now the second version of, or the second variant of Concat is one that we call in-place destructive Concat. This is a kind of weird one, but one that you can still specify inside Gospel. All right. So the idea is that in this case, you say that you are consuming Q1 and you are modifying Q2, right? So what this means is that, let's look into the post condition, right? Q2.view is updated exactly. Once again, I'm switching a little bit the Q1 and Q2 here. Sorry about that, but you get the idea. You still concatenate the two Qs, but now it's very important to notice that since you stated that Q1 is consumed, you lose possession of the pointer. So you can no longer keep using Q1, or in some sense it would be unsound that you could not prove anything about Q1 if you keep using it after a call to in-place destructive concat. In some sense, you invalidate Q1, right? And when it comes to translation into classic separation logic, you can see that in this post condition, right, you have no way to, or you do not talk about Q1. So if you are doing your proof in separation logic, or thinking about doing a proof in separation logic in this sense, so there is no way to after this post condition to keep the possession, or you lose possession of Q1. That's, in practical terms, that's what happens here from separation logic wise. Okay, and the final variant of the concat function is one that is a very friendly one. Okay, so it's not a non-destructive concat, and in some sense, what it's doing is that this is going to allocate a new Q with which is the concatenation of both the elements from Q1 and Q2, right? And the fact is that you do not lose possession of Q1 or Q2, and neither you are mutating them inside the non-destructive concat operation. So once again, there is no modifies clause over your arguments. So what we know implicitly is that these are read-only arguments, okay? And once again, in the post condition, these are implicitly returned. So you can still using Q1 and Q2 after calling non-destructive concat. Okay, so finally, let's look into a general or a more general example of this translation scheme. So let's pick an arbitrary data type T with two models, left and right, okay, of some type. It's not very important here, and a function that operates on a huge number of such arguments of such type. All right, so we call them P1, P2, P3, P4, and also takes an n as an integer as an argument, right? And returns also P5 and P6 of data type T. And so, once again, it's important to stress that all of these arguments are disjoint from each other, but also from the values returned by the function. So P5 is disjoint of P6, and both of them are disjoint by any other argument. Okay, so the precondition is P, the postcondition is Q, sorry. And what's important here is how you use the modifies and the consumes clause. Okay, sorry. So you say that you entirely modify P1, so it says that you change the value inside left and right. For P2, P2, you only change the left model. Okay, so you can do that, and you can actually get into that level of granularity inside Gospel, and you entirely consume P3. So if you want to write this or reason directly in separation logic, this is the the kind of triple that you need to write. You need to universally quantify over a bunch of variables, some to represent the pointers, P1, P2, P3, P4, others to represent the logical models, okay? X for the left field, Y for the right field, okay? And so in terms of precondition, you need to quantify over all the, or represent all the representation predicates, put some of them as read-only representation predicates, and finally you can see that on the post condition, you lose possession. There is no way to talk about P3, right? So for P1, you see that you have newly updated models, and P2 you keep the old right model. Okay, so that's what you need to write in the first place. Had you started doing this proof in separation logic directly, but with Gospel you can write this much more concise, much more readable specification, and you know that we took care to define this translation scheme into this triple. So that's what you get when translating Gospel into separation logic. All right. So now that I've presented you our specification language of the day, let's see how it has been used up until this point to verify OCaml code. Okay. So the Gospel specification language was born inside a research project called VOCO, which was aiming towards building a verified OCaml library, where we used three verification tools. And all of these were using Gospel in some way or another to produce OCaml or correct by construction OCaml implementation. But one important aspect is that Gospel was only tied to the specification of interface files. So in terms of Y3, this is a tool that is first order logic, or is built on top of first order logic and weakest precondition calculus. Verification conditions are sent to automated theorem provers, so it's a tool that is clearly oriented towards automated proofs, and its targets are imperative programs with limited mutability. What this means is that there is no particular memory model inside Y3, so you cannot deal with recursive mutable data structures. Only imperative programs where Y3 can tell statically every memory aliasing that is happening. Okay, but yeah. So with Coq, then the second tool, Coq, I think the Coq proof assistant is very familiar to most of you. So with Coq, we are targeting purely applicative programs, purely applicative data structures or algorithms. And in order to get OCaml code, executable OCaml code, we need to rely on the Coq extraction mechanism. CFML is a very powerful tool which features an embedding of high-order separation logic inside the Coq proof assistant, and you can use CFML to do proofs of very interesting OCaml programs, targeting pointer programs or high-order iteration, or other classes of programs are high-order iterations with effects. Okay, so there was the tools that were currently using Gospel as a specification language. But as I said, Gospel was limited to signature files or .mli files. And moreover, none of these approaches were entirely satisfying from my point of view. Why? Because if you think about Y3 or Coq, then once again, you need to write implementations on YML from the Y3 side, the specification and programming language of the framework, or on Galena when you are writing Coq, your proofs in Coq, and then extract proofs into executable code. So rewriting entire code bases just to verify them. Okay, yeah, it's sure that you can go, on the other hand, you could go from OCaml directly into proofs inside CFML. But since CFML is such a rich tool and features such a rich logic, all the proofs are interactive, so it's kind of very hard to work. I mean, it's not that hard to work with CFML, but it's kind of hard for someone which is not a proof expert. So it's hardly the choice of any regular OCaml programmer which does not have any a verification background. Okay, so that's how the Cameleer tool enters the scene. So we wanted to give a fresh view on all of this ecosystem, right? And so in a diagram, how does the Cameleer tool works? So on the left-hand side, you can see the OCaml dimension, right? And on the right-hand side, you see the Y3 dimension. So Cameleer works, I think you've guessed by now, works by translation from OCaml programs into equivalent ones in Y3. But what is very important here is that the programmer is entirely focusing on OCaml code. So these full boxes represent everything that the programmer needs to write by hand, okay? And the dashed boxes represent everything that is tool translated or automatically produced, right? So it is clear that the Y3 part is automatically produced by Cameleer, and the OCaml part is written by hand. So let's focus, or let's zoom in this Cameleer translation, right? So what we are proposing is that instead of using Y3 as up to this point, which means that you need to write code in YML and then rely, or doing your proof and then rely on the Y3 extraction machinery in order to get executable OCaml code. What we are proposing is that you go a level up and you write OCaml implementations, annotate it with gospel specification elements, and then using the PPX-lib infrastructure and an automatic translation, which is mainly the Cameleer function, you translate an AST issued by the OCaml parser into an AST on the YML side. And so up to this point, all of this is done entirely on the background, so the user is never aware of this translation scheme. And when you get to this point, you have an equivalent YML program, an equivalent to the input program, right? And from now on, you can use out of the box any tool offered by the Y3 toolset. So in particular, this means that you can interface with many different SMT solvers, for instance, Z3, AlterGo, CVC4, or when needed, you can still translate your proof into the Coq proof system, right? But everything is out of the box for you. You just need to worry about writing OCaml code and providing with a suitable gospel specification. Okay? Yeah. So let's take a look into this translation part. A few words before we started. So up until this point, we are supporting what one can call core OCaml, a subset of OCaml that I call core OCaml, which roughly corresponds to camel height, plus some support for functors, because functors are quite important in OCaml, so no way to write a verification tool for OCaml with at least minimal support for functors. So we leave objects behind. We are not supporting the objective layer of the language at this point. And other interesting features of the language, more type-oriented features like JDTs or polymorphic variants, are not supported by Cameleer either, neither by the gospel specification language. We also have a limited support for higher-order functions, okay? And this is constrained, imposed both by Y3 and gospel. And this means that we can only reason and deal with higher-order computations where the argument function is effect-free. So in some sense, you can call these pure high-order functions, okay? So things like each iter function over a list, we cannot do that because the argument function is supposed to perform an effect. We also have a limited support for mutability. Okay, as I've told you before, Y3 only supports reasoning about programs with bounded mutability, which we call it modern mutability, which in some senses forbids you to or avoids you to reason about mutable recursive data structure, because you could be writing data structure with cycles, and so you could not be sure of tracking all the aliases that statically tracking all the aliases that are happening on your memory. We have a technical report where we present this translation as a set of inference rules. But today, I want to give you an overview of the translation using a couple of practical examples. Okay, so before going into the examples, I think this is a good moment to look into the chat. Okay, I think everything is fine. Okay, so no questions on the chat. Thank you. Right, so now let's see a very first simple example of how this is done in Cameleer. Okay, so or how this is translated into Cameleer code, or sorry, inside Cameleer from OCaml to Y3. Very simple, even odd functions. These are most likely the first example of any mutually recursive definition that we learn. So the gospel elements are given inside these special comments after the function definition. And the first thing that the gospel infrastructure is going to do is going to translate this into proper OCaml attributes. So if you want, you could already write them in the first place, but I think it's much more readable if you write them as these comments. And the gospel and Cameleer infrastructure will translate them automatically for you. And so at this point, you have a valid OCaml program that you can feed to the parser. And then the Cameleer translation core will produce this YML program. It's very, very similar in terms of implementation, but what's important to note is that specification elements are now parts of the actual implementation. So you can see that the specification clauses are now outside comments. Okay, it is important to note that is in this example that in YML, let reconstruction is limited to to function definitions. So if you try to write a recursive list using let rec in OCaml, Cameleer will complain and will not translate such a program. You could still imagine giving it a gospel specification, but you will not be able to verify anything about it using Cameleer. Okay. So now, when it comes to loops, for instance, a while loop, it comes with no surprise that inside deductive verification you need to provide a loop invariant, okay, and also a variant which ensures loop termination. So in this sense, in this example, sorry, this is the computation of an integer square root of the argument. So you provide with these 3 lines invariant, and so this is going to be slightly changed. The attribute is going to be attached to the while keyword, so we need to change a little bit of place, but it's still automatically done for you. And now, once again, you have this valid OCaml program, and Cameleer will now be happy with you and translate it into this very similar YML program. Yeah, YML and OCaml share many syntactic and semantic constructions. All right. So now, moving on to more verification and specification aware elements. So let's imagine that you have a definition, or you wrote an OCaml function that is the textbook definition of Fib, the Fibonacci function. Well, this is not a very efficient implementation, we know, because of repeated computations, but it's still one that is very usable as specification. So with Cameleer, you can tag it as a logic function, which means that you can use Fib inside specification of other functions, for instance, here in Fib main, right? And as ghost, because you say that, okay, this function here has no proper execution purpose, it's only here for easing specification and verification, so it should be raised before producing compiled code for this OCaml program, right? So that's what we call a ghost function. on deductive terminology. Also, you can take some arguments as ghost arguments, because this n here of fib ox is only the first argument of this function is only used to produce a more simpler specification and proof. So it has no interesting purpose whatsoever from the executional point of view. So it should be erased before compilation. When it comes to the YML side, you can also tag some function as ghost, and function here on the YML side is the keyword to state that this is also a logical function. Okay, so you can use it on the post condition of fib main. Okay, so now imagine that you want to build a type of non-empty list, a type where you are able to prove that you only use it in a scenario where these lists are non-empty. So you define a new data type using a record, right? And you can attach what we call the type invariant to this declaration, one that says that this field self is always different from the empty list. And when you write your head function, right, then you know that the first branch of the pattern matching is a one that is unattainable, right, unreachable branch in your code execution, right? So you mark it with assert false, and luckily enough, on the YML side we have this absurd construction which has exactly the same semantic as the asserts false. It is used to mark unreachable points on your code, and yeah, we all know that assert false is already treated in a special way by the OCaml parser, by the OCaml type checker. So it has it's good that on YML we have single keyword or single construction that has exactly this semantic. In terms of type invariants, yes, of course, on YML you also have those. Once again, these are part of actual implementation and not surrounded inside some comment. All right, so now up until this point, I've shown you how to translate the core language, let's call it like that, from OCaml to YML. Now it comes the interesting part is dealing with modules, because that's where the OCaml and YML language differ the most, right? And the thing is that the OCaml module language is much more expressive than the YML one. So in particular, you do not have such thing as a submodule inside Y3. So imagine that this module mult is built inside or is contained inside a larger file, a larger OCaml development. So this would be a submodule on the OCaml side. So what you're going to do is that Cameleer is going to translate this into a scope on the YML side. And scopes should not be confused with submodules. Scopes are just for namespace management purposes. So yeah, there is no such thing as a submodule on the YML side. Okay, but you can still simulate it. Some OCaml submodules using very carefully scopes on the YML side. And even more interesting is when it comes to functors, because there is no syntactic support or even the notion of functors on the YML side. So imagine that I have this part of the of a leftist heap implementation that I took from the OCaml containers library, right? With no surprise, this data structure is implemented as a functor make, which takes a partial order as a functor argument, right? So what I'm going to do, or what Cameleer is going to do, is that it's going to produce the following structure on the YML side. The functor make is going to be turned into a scope make, and the functor argument E, right, this one here, is turned into a nested scope, okay, with all of its elements inside scope E, right? And so what happens is that when you nest scopes like this, so imagine that I would have a bunch of other scopes, F, T, and so on. Cameleer and Y3 would be considering these like functor arguments, okay? So everything inside of them must be non-defined types, abstract data types, and non-defined functions, right? And so after closing scope E, you can still write in the code as before, namely you can qualify the using the dot notation about the elements that come from the argument E. This translation is exactly the dual of how Y3 is extracting functors. So if you write your proof and your implementation directly in Y3, you need to write this here if you want Y3 to be able to recognize this as a functor and extract functorial code. All right, let's look into a first demo in this tutorial. Once again, this is a good opportunity to see what's going around on the chat. Yeah, everything is still very, very quiet. So let's take a look into a very simple shor-based cipher implemented in OCaml. Okay, so I have here this OCaml development file, and what you see is that I have three gospel constructions. Okay, so I'm going to use sequences from the gospel standard library, right? And the module from the also gospel standard library, which provides me with the coercion, or there is a function that translates lists, OCaml lists, into sequences. Sequences should be considered like mathematical lists, so these are pure data structures, but one that you can where you have direct access to the elements of the sequence using integer index-based access. I wrote a predicate map, which is a higher order predicate, so that's perfectly fine. Everything is effect-free, and you can see this like a map to a combinator. I've called it just here map, which says that using this f function, I'm going to combine the elements of the A1, A2 sequences to produce a result sequence of type beta sequences when the arguments are alpha sequence. Both arguments should have the same length, but also they should have the same length as the result. And very simply, what I'm saying is that for every element within the bounds of sequences, right, of A1 and both A2, of course, the result of RA is exactly applying F to A1I and to FA2I. Okay, so you'll see that this will come in hand in a couple of minutes when I'm going to write my specification for this example. So what I'm trying to do is that now let's imagine that you have a module shor, which implements a shor operation over an element of type T, and somehow you want to implement a cipher mechanism using that shor in a way or another. So in this case, you have the elements of your message, the type T, which will represent your message, and a very simple function that will cipher your message, cipher and decipher. Okay, so now if I try to, or I begin to write my my module make. Okay, so I take as an argument x of type shor, right? And so I must implement a module that instantiates cipher. So at this point, I'm very happy to be building this inside OCaml because I have very, very cool tools, like for instance, Merlin, that statically is telling me that I'm not entirely complying with the constraints of the cipher module. Okay, so that's yeah, you're right, Merlin, because I have not yet implemented the cipher function. So first things first, let's give a definition to type T, and I'm going to make it a list of ELT values. And so when I'm implementing the type or the function a cipher, what I'm going to do write this as a recursive function which takes the key of the cipher and the message. And so what I'm going to do is that, of course, I'm going to do a pattern matching. It's almost the case when you're writing a function in CAML. So when both the message and the cipher, when both the message and the key are empty, so I'm returning the empty message, the empty list, right? So when there is something yet to process, let's say that both bits are non-empty. What I'm going to do is that, so I'm going to short them, of course, I'm going to sort the head of the lists, and I'm going to recursively keep doing this by calling the tails of the list. Now, when I save my file, Merlin once again is my best friend and tells me that you still have some cases that are not covered in your pattern matching. What happens when both, or what happens when maybe the key is longer than the message? What to do in such case? So I'm going to take a decision here. So I'm saying that there is no such case. I'm going to assume that key and message always have the same length. So I'm going to say that this is an unreachable point in my code, and Merlin is quite happy with me. He says no errors. Okay, so I've implemented my make functor. Let me try to call Cameleer now on this very simple file to see if everything is okay. I think I've done it all right. So I believe that my code is sound. So I'm calling Cameleer space the name of the file. All right. Oh, sorry. Yeah. So he tells me that I still need. I'll explain this in a minute. So let me just state, that this function here is a terminating one. Sorry, I'll explain this in a minute. So this is a recursive function which decreases in the length of the key. All right. Yeah. So he's happy with me now. So what happens is that when I call Cameleer, right, I'm immediately presented with the Y3 integrated development interface, right? So on the right-hand side, you see the code. On the left-hand side, you see your proof tree, okay? And your proof tree, you have the nodes that corresponds to the things that you are trying to prove, or in other words, the verification conditions. So if you're going to look into this task, this is exactly what Y3 generated. Of course, that Cameleer turned in the background, so it generated a YML file in memory, fed it to the Y3 compiler, and the Y3 VCGen was able to produce this verification condition, and which is represented by this goal. And everything else is the local context or your proof context. So the task is exactly what is sent to SMT solvers to try to discharge, right? So one thing that I always like to do is that when I have these kind of proofs that are based on a bunch of cases, right, this pattern matching here, the first thing that I want to do is to split this VC in more simpler ones, right? So I wrote split VC in this interactive bar. And so now I see that I have more precise description of what I'm trying to prove. So at some point, I'm trying to prove that this yellow part here, so this is an unreachable point in my code. Another one that one I'm calling recursively cipher. This is actually a variant, a good variant. The length or the structure of my key is decreasing, okay? And then once again on another case, I also need to prove that this is an assert false or unreachable point in the code. So maybe this one I can look into the task. All right, this one is the case where message is nil but key is not nil, or the empty list. And this is the case where message is still a const but key is a nil or an empty list. Okay, so I have two cases. That's not surprising. So when I get back here, if I select this split VC node, and for instance, I get back to my interactive part, I call AlterGo, a very nice SMT solver. Well, it's actually able to say that my function recursive calls are terminating, right? But it's not able to prove that this is an unreachable point in the code on neither occasion. So let's get back to the OCaml file. Well, this comes with no surprise because I've never said that I'm assuming that key and message are lists of equal length. So let's put that as a precondition, right? So let's say that, sorry, I can use length directly because this length here applies to sequences. And since I have a coercion from lists into sequences, that's pretty okay to use the length of sequences. So let's say that the length of key is always the length of message, right? So now I get back to the Y3 development part. I press Ctrl R, or I can do Let me see where I can reload my session. Yeah, there should be somewhere. Yeah, save and refresh session, Control R. So what this does is that this is going to, on the background, is going to call Cameleer, which takes the new specification and translates it into a new specification inside YAML. So now let's go back to our proof. So now let's see what happens when I call alter go inside this node. So it gets green, right? So now I'm able to prove the unreachable point. Also, the variant part was already proved. So let me press R on my keyboard. Yeah, it reloads the proof or reruns the proof, and it's done. It's still doable. So now the other assert false or the other unreachable point, it's now good. And so what about precondition? In this case, I need to maintain the precondition when I'm calling cipher recursively. And of course, you've guessed that this is actually a very, very easy one because I've decreased the length of both lists by one. Okay, so yeah, it's happy with me. Yeah, so everything is green about the cipher function, which means that this implementation meets the specification that I gave it. But one thing that, yeah, it should be interesting for at least to be sure that I'm doing things correctly. What about if I write a correct function, like for instance, one that calls twice the cipher routine, right? Okay, so I'm not changing the key, but I'm only changing the message. So what I'm trying to say here is that from a proof perspective, we call are the result of this function, and I'm using smaller names inside the specification. So Cameleer will be happy with me calling that differently. So first and foremost, I need to say that, yeah, of course, P and M are lists of equal length, right? Because when I'm calling cipher twice, he will ask me to prove the precondition. We'll see that in a minute. And so in some sense, as a post condition for the correct function, what I want to say is that R is the exact same sequence, is the exact same list as the input M, right? So getting back to Y3 after writing this specification, Control R again. So now the cipher is still proved. So now I have a correct function to prove. I press S, and this does a split automatically for me. Okay, so now I have a bunch of preconditions and postconditions to prove. What I can do is that I choose split here. I type alter go, and what happens is that only the first precondition is proved. Yeah, the first call to cipher, which comes with no surprise. Yeah, because I've never attached a post condition to the cipher function. So for this case, he's telling me that, okay, the length of Q should be the length of R, but I know nothing about R, the result of calling the first time cipher. So what I need here is to attach a post condition to my cipher, and that's where I'm using the map predicate that I've shown you before. And in some sense, I want to say that map or the result sequence is mapping or combining the two input lists using a shor that comes from the functor argument, and which produces the R sequence. All right. By now, I'm trying to use shor, a programming function inside specification. So what happens here from the Cameleer side? So if I get back to Y3, Control R, and I see that, yeah, the unbound function or predicate simple XOR. So what I need to do is that I need to get back here, and as seen in the slides, I need to attach a logic attribute in order to say that this is indeed a function that is effect-free, and you are able to use that inside the logic as well. So getting back to Y3, I do Control R, and now he's happy with me. Okay, let's see if I can still do my proof of, sorry, AlterGo is not my friend here, so let me call CVC4 instead. Yeah, so he has quite a hard time proving the post condition. So what I can say is that I'm going to split once again, because if I look into the task, there is still quite a few cases to do. So splitting again does me a case analysis function, right? So I get smaller verification condition. So let me try to call CVC4 once again. And now he's happy with me. So in some way, I help CVC4 closing this proof by doing case analysis, destroying this pattern matching here. Okay, now getting back to correct, let me check if now calling AlterGo on this one. Yeah, sorry, AlterGo gets a little bit confused sometimes. So let me call CVC4. Okay, so now the preconditions are good. So the second precondition is okay because I've told as a post condition that this is a map. So which says that, yeah, everything keeps the same length. So it's okay for the precondition of the second call. What about the post condition? Yeah. What about saying that these are the exact same sequence as before? The fact is that I've never ever said anything about the property that is expected from the shore function of the functor argument. So what I need is that I need an axiom, okay? Maybe to say that my shore is an involution, right? What this means is that for every element, when I do this, I apply short twice, I still get x, right? So this is what means for a short to be an involution. So is this enough? So let me go again, Control R. Okay, the proofs are lost. I press R just to say that if I can get back to my proofs, cipher is still okay. But yeah, let's try the post condition here once again. No way with CVC4. Let's try Z3 because I have a bunch of installed provers. So neither CVC4 or Z3 are able to finish my proof. So at this point, I'm pretty much convinced that my specification is not good enough, right? So yeah, and he's right because I still need a second property about the short, another axiom. I'm going to call it short com, and you can guess that this says that the short operation should also be commutative. Okay, so I am stating that is right. So once again, I save my development. I get back to Y3, Control R. So once again, I need to replay everything because the context changed. So Y3 is not able to be sure that the proof is still doable. So now let me call CVC4 on the all correct function. Okay, so yeah, and now he's happy with me, right? So now I've been able to prove that after calling cipher twice, I get the exact same result as message, as input message, everything thanks to the fact that I've updated my specification with some properties about the shore operation. But what about this node here? So this node here is talking me about a refinement of make, right? So the thing is that I've constrained make to be a module of type cipher. So in some sense, I need to prove that the operation that I'm showing to a client of this module, right? Its specification should be an inclusion of should be included in the specification that I gave to the implementation part. And in practical terms, this means that the preconditions of the interface should imply the preconditions of the implementation, and the post conditions of the implementation should imply the post conditions of the interface. Well, if I get to the task, what I'm saying is that I need to prove that, yeah, the precondition of the implementation part, the lists are of same size, right? Well, it's not provable because I've never attached any kind of specification to the cipher function itself from the interface. So let's do it. Okay. So let's try to propose a specification for the interface function. So let's name the arguments x and y. Yeah, why not? And now let me try to put a proper specification, right? And one that should be very, very close to the implementation one. So, okay. So what I'm saying is that I need to say that, yeah, the length of the arguments are the same. Oh, but the fact is that at no point I know how to compute the length of x and y because they are elements of type T. Yeah, that's for sure. So So no way this is a type, so this is not typable, okay? So this doesn't type check. So what I need to do, and I can do in Gospel and Cameleer, is to attach also, or to say that there is a function called toSec, right? So one that is going to translate elements of type T into sequences of ALT values, right? So, and this is just a function that I say that, well, it exists. Trust me, there is a function here that translates elements of type T into sequences, right? And so now I can use the such function to do things like this. So this is not a coercion, so that's why I need to write it every time, right? So now, since this is Cameleer and not only OCaml, inside the module, since make is constrained by Cypher, I also need to provide an implementation for toSec. So in this case, it's actually very, very easy, right? Because it's simply a matter of calling the off list that I got from opening sec of list module from the Gospel Standard Library, right? And applying it to the argument. Okay. All right, so let's do a Control R again. So the proofs are lost once again. This is a default from Y3 because it's very, very conservative. So I press R. And yeah, let's hope everything is still green again. So what about now? So now I have a precondition of my interface. So it's displayed in green. So I'm assuming the precondition in the interface, and I'm trying to prove the precondition on the implementation side. And since the toSec function is here implemented as off list, if I go to the task, now you can actually, or we can actually hope that this is provable. So let's try with CVC4. And yes, right? So CVC4 is pretty happy with me and is able to close the proof. So now I can say that I have not only proved my module, but also I can say that this constrains soundly the module Cypher. But can I also attach a postcondition to Cypher? I mean, one that can, because my clients will be mainly looking into this module type to get information about the function Cypher. They're not entirely supposed to look into the implementation. So let's attach a postcondition to this one. So in this case, the proper postcondition would be to somehow use map. But now I need a SHOR operation, right? And I need to say that this SHOR operation applies to the sequences K and M, or the transformation into sequence of lists K and M, and also the result of this one. Okay, sorry. Yeah, but I have no such SHOR operation, right? So once again, we do the same trick. So we say that, yeah, trust me, there is somehow, or there will be at some point, a function that takes two elements of type ELT and returns a new one, and I call this a SHOR. All right, so remove this one, get back to Y3, do a Control R. Sorry, yeah. Oh yeah, sorry. In this case, it's not MN, it's S. Sorry, wrong naming, but no problem. So now I do Control R. Yeah. So he's not happy with me up until this point because now once again in the make I also need to provide an implementation for SHOR. Yeah, no worries, I'll do that. Don't worry. Okay, and everything is pretty straightforward at this point. So just to say that the expected SHOR of the interface is the SHOR that comes from the argument of the function. Okay, so once again, I lose my proofs. Let me do a Control R just to be sure. So everything is okay inside the SHOR module, right? And now what I'm trying to do is that I'm trying to prove the refinement of make. So to say that make correctly implements Cypher. And now I do a split. Not only I have the precondition, but I also have the postcondition. And in this case, it's the postcondition of the interface that I'm trying to prove. Let's call it CVC4. Sorry. Everything is green, right? So also the postcondition that I've provided to Cypher is one that is respected by the implementation. The last thing that I want to show in this demo, because time is running shortly, is now what happens if I try to build some modules that are of the type of the expected functor argument. So let's imagine that I do a module that's called xbool. So I'm explicitly saying that this should implement the short constraint. So in some sense, should provide a type T and a logical function short, a logical and programming function short, sorry, one that I can use inside specification, right? So type T would be, as you get, bool, and my sorry, I'm getting tired here. So I need to say that, yeah, what about saying that if X, then not Y, else Y? So this is the first implementation of a short function over Booleans. What Cameleer can help me now is in make me sure that this xbool module actually respects the constraints imposed by short. The OCaml parser, and in particular Merlin, are my friends telling me that, yeah, in terms of OCaml programming code, the OCaml programming part, you can be sure that you are respecting every constraint of module short. In particular, you are implementing type T and function short. But in some sense, now your short function must respect or must implement these two axioms, right? So let's get back to Y3. Let's reload. And now, yeah, I've lost my proofs once again of refinement make. This is Y3 working, yeah. So I now have a new refinement, which is called xbool. Okay. And in this case, what xbool is trying to refine, now I need to prove that my implementation of short, an actual implementation, respects both axioms. Okay. So now I can, yeah, the task is not very interesting at this point. So let me get back to my CVC4. Yeah. So it's happy with me. So it says that I've implemented a good a commutative function. Is it an involution? CVC4, and yes, it is. So this is a good implementation for a short function over Booleans. I can think about a new one, right? Maybe let me do a second one, also with Booleans. But in this case, let me say something equivalent to the first one, of course. But let me write it in a slightly different way. So instead of using a if then else structure, I'll use it like this. Okay, so either X and not Y, or not Y and X. Okay, getting back to Y3. Proofs a lot, sorry. Yeah. Back here. And now the new implementation should also be commutative and involutive. So CVC4 on both axioms. Yeah, so I've done something stupid here, right? What I've done wrong? Yeah, maybe I said something. Yeah, sorry about that. Yeah, so you see that I made a mistake. So Cameleer and Y3 are my friends. This was not done on purpose, I assure you, but it still helped me to understand that this was not a commutative one. So I think I fixed it. So let's see what happens now. Yeah, so now both of them are approved and the other ones remain. So everything is green, and I'm pretty happy that I was able to very easily understand why my implementation was not a good one by means of deductive proofs, right? And so, yeah, just to conclude, another example, a more, let's say, artificial one. Let's imagine that now type T is not a base type. Let's simulate bits like this. And so my, right, so I'm doing my short via pattern matching. And yeah, when both arguments are the same value, so this should return 0, and on any other case, this should return 1. Okay, yeah, so I close Y3 by accident, sorry, so let me call Cameleer once again. Yeah, so everything was pretty much lost, right? So the new refinement yeah, I'm pretty sure that this is going to work. So let me call CDC from the old refinement, and everything is green. So I've just done a very, very simple example in order to show you not a very sophisticated OCaml code, of course, but in some sense, how Cameleer or using Cameleer with a combination of static tools for OCaml like Merlin in particular, can help me to be sure that I'm developing correct by construction modular OCaml implementations. All right, so let me wrap up this first part of the tutorial by giving you a brief summary of some of the case studies that I've been able to prove with Cameleer up to date. I've put an effort to verify programs of different nature, ranging from applicative data structures, ephemeral data structures, array scanning algorithms like searching and sorting, mathematical-oriented functions, some historical algorithms like Boyer-Moore majority routine, effect-free higher-order implementations like OCaml list fold left and height of a tree implemented in CPS. Okay, and up to date, the more interesting, I'll say that the most interesting example at this point is the unified implementation, because it features a very interesting specification and implementation, but we are able to do this fully automatically. So even if it's a very, very interesting proof, it's done and fully automatically. You only need to do a couple of splits and then call SMT solvers. No need for interactive steps on the Y3 IDE. And the larger development to date is a small compiler from arithmetic expressions into a stack machine, following what is described in the textbook by Nielsen and Nielsen. This is not a particular difficult example, but one that takes a couple of implementation tricks, and moreover a couple of specification tricks where you mix calling specification inside the implementation to help SMT solvers do proof by induction. All right. So in order to conclude, I've been developing and presented you today a verification tool, a deductive verification tool for a representative subset of OCaml. I'm quite happy with it. And I've been able to verify a good number of case studies. Most of these are fully automatically verified. In the future, it could be interesting to write a proof or soundness proof from OCaml into IML. I mean, one that shows the semantic preservation from OCaml into IML. This poses a number of interesting issues. The first one is to build an operation or a formal semantics for OCaml, right? And perhaps more development oriented into the tool itself would be to target heap manipulating programs, right? Because up until now, I've not been able to deal with heaps because Y3 does not support it. So Cameleer will not be able to translate it into Y3. So I'm currently working on extending my translation function from core Cameleer into a support for the Viper intermediate language, one that is intermediate language supporting separation logic, formal separation logic, but also interfaces with SMT solvers. And when it gets to the point of verifying high-order effectful programs and very complicated arbitrary pointer programs in OCaml, then I will need to turn into CFML. But it's still very usable because CFML features such rich set of tactics that one can very easily or more easily writing proofs, even if these are interactive proofs, but it's actually much easier when compared to other tools to write proofs inside CFMLs. And the main question that I put to myself is that Cameleer is now ready to tackle even larger case studies. I'm pretty confident that we can, and that's actually what we are going to present on the OCaml workshop. A quite large development that is to prove the actual implementation of the set module from the OCaml standard library. All right. that's pretty much it for this section. We are closing up just on time. That's pretty cool. So in half an hour, what I would like to do with you is that I'm starting by reviewing Cameleer installation and user procedures. Okay, if you want to try Cameleer on your own, right? And after that, I'll be mainly using time to present exercises / examples, whatever you want to call it. I hope I have time to present these 4 examples. I'll start with a very simple pure replicative data structure, then some examples where you need to, or you are, when you are doing array scanning as a OCaml function, so you need to provide a proper loop invariant. Yeah, spoiler alert, I'm doing this with a while loop. Then I'm going to show you a possible implementation for the queue data structure that I've been talking about today, and how to prove it with Cameleer. Okay, and if time allows, I would like to briefly present our proof of leftist heaps, and this is exactly the code that is shipped inside the OCaml container library. So it's actually an OCaml implementation that is widely used. So it makes an interesting case study for the tool. Okay, yeah, just to wrap it up, if you got interested and you want to get more details about the tool and the project, the Cameleer project, you can take a look into our CAF paper, which was presented last month. And yeah, the GitHub link for the old development is even below. We'll be looking at this GitHub repository first thing next session, but feel free to also take a look during the break. Yeah, so that's pretty much what I wanted to show you in this first session. I'll gladly take questions, and if you want, you can also use the break to answer questions. So yeah, go ahead. Let me check if there is something happening on the chat. I don't think so. Yeah, so any questions? No? No questions? I hope this was not too boring. Yeah. Yeah, sometimes you tried, yeah, let me try to, Rui, do you want to, yeah, let me invite you to stage and see if you want to, okay, do you want to put your question lively? Because I think that's preferable for live transmission.
All right, can you hear me?
Yeah, perfectly.
Yeah, I think sometimes you tried 3 solvers like D3, CDC4, and Ergo. So why do you do that? Do you have some insight about solvers?
Yeah, yeah, that's a pretty, yeah. Thank you for the question. That's an excellent question. So so let me remove you from stage because that's how the organizer told us to do. Yeah. So thank you again for your question. Yeah. So the idea is that Y3 is able to interface multiple SMT solvers, not only the 3 ones that I've shown you here, but a bunch of others, and that's the difference comparing to other verification tools. And the things that we are doing that in Y3 because we know that some SMT solvers are better or more well fitted for some purposes than others. For instance, AlterGo is able to support some form of polymorphism, which, for instance, Z3 and CVC4 do not easily support. I think that's not entirely true with the new developments of SMT-lib, but that was one key aspect when using AlterGo to try to finish proofs that involve some kind of polymorphism, right? But the very honest answer to this is that, okay, I know that I'm using Y3. This is a tool that is able to interface with many different SMT solvers. So in practice, what I'm always trying to do, and I'll show you in the second part of this tutorial, is that I'm going to press a button on my keyboard, and Y3 is going to run the three main SMT solvers one after the other, and if one finishes the proof, then I'm happy. Okay, so in some sense, it doesn't matter the SMT solver that you choose. I'm happy if one of them is able to finish the proof. Yeah, if you are very, very aware of a very particular case where one of them is much better than the other, then you can only use that one. Another example would be with AlterGo. AlterGo supports pattern matching, or better support for pattern matching than the others. So maybe in very, very complicated pattern matching cases, you need to AlterGo. But in practice, and this is a very honest answer, believe me, is that you are going to try all of them. For instance, I have also eProver installed on my machine, which is an SMT solver, which is very good for finishing proofs with existential quantifications. So what I'm doing most of the time is that I try AlterGo, then I try CVC4, then Z3, and then maybe eProver. If none of these is able to solve my verification condition, then at that point I say to myself, okay, there is something wrong with the implementation or the specification. So it's a very try and error approach. Are there any other questions, or everyone is willing to take the break? Okay, let me see. Yeah, so I think there are no further questions at this point. So okay, I think we can take a break. So I'm putting the session on break, and so according to schedule, yeah. But of course, feel free to put questions anytime on the chat. I'm also sharing with you my email address. All right. So if you also want to send them by email, so feel free to spam me with any questions that you might have. So yeah, let's take a break. And as I was saying, according to schedule, we should meet in 27 minutes. So Paris time, this will be 1 o'clock, right? Yeah, 1 p.m. Okay. So my time, Lisbon time, will be exactly by noon. Okay. So yeah, see you in a couple of minutes. Thank you, and thank you very much for your attention. Thank you for watching, and I hope that you can follow or keep with us for the second part. Sorry. Yeah. See you. All right. So we'll be starting the second part of this tutorial in 5. Okay. So yeah, in the meantime, I'll wait for people to join. I hope you enjoyed the first part, of course. Just a gentle reminder that we'll resume in 2 minutes, okay? That's why we are still waiting for people to join. All right, so thank you for coming to the second part of the tutorial on deductive verification of OCaml programs in Cameleer. So it's time. So let's get started. I hope you can hear me well. Can you just say something on the chat if you can hear me well? I hope you can. Yeah, thank you, Rui. Okay, thank you. Yeah, let me share my screen once again. All right. Yeah. So for the second part of the tutorial, it will be a much more hands-on experience, if you want. What I'm going to try to do is to show you a couple of examples where I'm going to be writing either OCaml implementation, gospel specification, and in some cases both of them. And during the entire period, we'll be using Cameleer to translate it into Y3, and then trying to prove, right, that the implementation meets the attached specification. Okay, so I hope I have time to go into details in all the four examples. If not, no worries. I'll put those online with the instructions to replay them. So let's start by taking a look into the Cameleer installation and usage procedures. So I would like to call your attention to the OCaml Gospel organization inside GitHub, where we have a couple of projects that are currently using Gospel as its main basis. So it's kind of the ecosystem or under development ecosystem for around the Gospel specification language. So one of such projects is Cameleer. So let's take a look. Okay. So if you are curious enough, you can go into the examples folder, and every example should replay with the current state of the tool. So feel free to try any of these examples. By the end of the tutorial, I'll give you again the link to this GitHub repository, but I also gave it by the end of last session or the first part slide, the last slide from part 1 of this tutorial. So Cameleer depends on the Gospel project, with no surprise. We do not currently have a PAM package for Gospel, so you need to do a couple of git hack yourself. So you need to clone a specific branch of Gospel, which is called implementations_gospel. Okay, and then you can pin that repository, which will install the Gospel type checker and infrastructure. Okay, so after that you can clone, because we have not yet released also a CAML package for Cameleer. So you can clone this very same repository for Cameleer, you pin it, okay, and then it will automatically install Cameleer and all the needed dependencies. In particular, it will install Y3 if it's not yet installed on your machine, right? One thing that you need to do outside of all this process of installing Cameleer and Y3 is that you need to install SMT solvers or external theorem provers by yourself. So I would say that you need at least AlterGo CVC4 Z3, and it would be okay with these three, and you'll be able to prove any example from the gallery inside this GitHub repository, right? But you can also install Coq. Everything is very well explained in this page here. I will not open it, but it's kind of a very exhaustive tutorial on how to install such SMT solvers and then how to tell Y3 to detect them. Okay, then running Cameleer is actually a very simple process. Let's imagine that you write this very, very trivial OCaml function together with some very simple form of gospel specification. Then this is as easy as typing Cameleer space example.ml if the suc function is contained in a file called example.ml. Okay, I also included inside this GitHub repository a Vagrant file if you want to build from scratch a new virtual machine where you can very safely use Cameleer in a very contained environment, if you want to call it like that. Okay, and the Vagrant file does all the installation and the dependencies for you. All right. Okay, so let's get started with the first example. Okay, so this will be most likely the longest example of the tutorial because I really want to show you a couple of nice features of Cameleer, and I want to take my time in order to explain you well all the features that I find interesting. Okay, so once again, at any time, feel free to interrupt me because I'm not able to see what's happening on the chat. I'll maybe checking the chat from time to time, but yeah, feel free to interrupt me and to talk if you if you can, right? To put questions. All right, so in this first example, as I was saying, is going to be the longest because not only I'm going to be typing gospel specification and doing the proof, and for this very case, I'm also going to write the OCaml implementation part. Sorry. My goal in this tutorial is not to write very sophisticated or very, very complicated OCaml code and then do the proof using Cameleer. My goal is mainly to show you how you can easily write your proofs using Gospel and Cameleer. And by the end of the tutorial, I hope you agree with me that regular OCaml programmers can do such proofs, even if they are not super experts on deductive verification. Okay, so for this first example, let's take a look into this simple mutually recursive definition of tree and forest data type. So this is a polymorphic tree. So it's either the empty tree or a node which contains the value, okay, storing that node, and a forest or branches of descendants. And the forest is simply a list of trees. So it's an array tree. You can have more than two descendants, right? So now this might seem like a very, very simple data type, but it's exactly the same data type that is used to implement a very interesting variant of heaps, which is called pairing heaps, a very efficient one. And it's also proved using Cameleer, and you can take a look at the examples folder on the GitHub repository. So it's not a completely artificial data type, this one. It's actually very useful. So now that I have the data type, I can amuse myself writing some functions, like for instance, is empty, and I'm going to suffix my functions with _tree, Okay, and so the first thing that I can do on a tree is actually to say, okay, is this the empty tree, right? So if it's the E construction, yes, it's the empty tree. On any other case, it's not the empty tree. All right. So now another thing one is one that builds a tree of a single node, right? So one that has no descendant. So it's actually only contains the argument x. Now, finally, I can do one where I have an arbitrary tree, but I still want to add the x or a new element to the tree, right? So what I'm going to do is that, with no surprise, I'm going to do a simple pattern matching if the tree is empty. So I build a new tree. All right. So at this point, you see that I could call singleton because it's the same code. I'll do that in a minute. Okay. Then, if on the other case, if this is actually a non-empty tree, what I'm going to do is that I'm going to keep my root, or the root value, if you want to call it like that. And now, yeah, I'm going to call singleton tree here. What I'm going to do is that I'm going to build a new tree, and I'm attaching this as the first son of the current tree, right? So very simple data structure, 3 very simple functions that operate on top of such a data structure. Now, once again, let me call Cameleer on this file. So this is the x1.ml file. Is there anything to be proved? Yeah. So the thing is that when I see the the Y3 integrated development environment, well, I see that everything is already green, so there is nothing to prove. Yeah, that comes with no surprise because actually I have done anything about specification, right? So once again, if I get back to Y3, the task is just the empty task, so nothing to prove, no verification condition of really sorry, no generated verification condition. Okay, and so now let's dig into the fun part. Let's add some gospel specification elements. Like for instance, let's try to write the specification for the isEmpty3 function. So in this case, it returns a boolean, right? So I'm calling my result b and naming my argument t, right? I can name it whatever I want because it's not even named in the function definition, right? And so as a puts condition, what I can say is that, yeah, so it returns true if and only if what? Well, if and only if t is equal to e, right? So this is a possible puts condition for such a function, right? So let's get back to y3, and in this case, it will control r once again. And now I have a small task, okay? And so let me try to do this with AlterGo. And everything is proved, even without doing a split. Let me just see what happens with a split. I have 2 post conditions, or it means that I have 2 possible cases, okay, inside my function, which means that either it's this branch or the other one. So that's why I have 2 post conditions, right? So now let me try to prove these 2 using CVC4. So both CVC4 after split and AlterGo before split are able to finish the proof. So let me see if now, for instance, another one, Z3. Is Z3 able to prove this very simple specification even before splitting? Yes, it is, right? Now, let me remove the split part and go for a CVC4. Also, CVC4 is able to do it. So from now on, during this tutorial, let me erase these proof attempts. I just called touch delete on my keyboard, right? And so from now on, what I'm going to be doing during the tutorial is to press the 0 key on my keyboard. And 0, what it's going to do, it's going to run CVC4. If CVC4 with 1 second timeout does not complete the proof, calls Z3 also with 1 second timeout. If Z3 is not able to finish the proof, it calls AlterGo with 1 second timeout as well. Okay, so if any of this is able to finish the proof, then okay, I'm happy and I'll move on. Okay, so in this case, it was already CVC4 the one that was able to do it in about no time, but with a considerable amount of proofs and rewriting steps. All right, so the thing is that I'm not entirely happy with this specification. Okay, yeah, I mean, it captures the cases where indeed the isEmpty tree function will return true, but I'm actually providing too many details about the implementation of the data structure. Itself. So I mean, do I really want to keep this kind of specification so precise specification, right? It should be. We should be. Our aim should be towards a more declarative and much higher level specification, and not so tied to particular implementation details. So one thing that I can do is to introduce a logical function like this one, which captures logically what it means, the size of a tree. Right? What's the size of a tree? What is the number? How many nodes does a tree have? Okay, so you can guess this is a very simple, straightforward implementation, right? Okay, so the thing is that when it's the empty tree, it doesn't have any element. All right, so when it's not empty, what I'm going to say is that I'm going to add 1 plus the size, the size of forest, okay, of L. Not yet defined size of forest, as you have guessed. This is, of course, a mutually recursive definition, one that is also a logic definition, okay? So it is now the size forest, okay? And for such case, if it's the empty list, no new node to account for. And when it's not, right? So what I do is that I call size tree on the node, right? On the first node of the forest, and then recursively call size forest for the remaining of the forest, okay? And so now, since this is a logical function, I need to show that this is a terminating one, all right? Because if it's not a terminating function, it's up to no good use because it's not a total definition, so it would be unsound to use this size tree and size forest without actually proving that these are terminating functions. So what I'm saying is that, I'll start from the bottom, and I'm saying that size forest of f, naming my argument f, I'm providing the variant that says that, yeah, at every recursive call, the forest f structurally decreases. In other words, I'm calling size forest recursively over strictly smaller lists. And the same approach applies here, size tree, while I'm calling my size tree the argument t, right? So also for each recursive call, I mean this one here in particular, it will be over strictly smaller, structurally strictly smaller, this is hard to say, trees. Okay, so let me see if now, getting back to Y3, I do a Control R. Now I have new verification conditions. Let me do a split over both of them. So I put myself here, press S. Right. So for the first one, we need to show that this is indeed a terminating measure. All right. So let me press 0. And once again, it's CVC4 that completes the proof, right? And now for the other one, size forest, right? It's also a terminating measure, but this one is a little bit more interesting because we are recursively calling size tree, all right, the other function in size forest. So we are recursively calling size forest directly and implicitly also calling size forest because we are going through a call from size tree to size forest probably. So that's why this verification condition is a little bit more interesting. So now once again I press 0, and CVC4 is able to discharge both of them, right? Okay, so let's get back to the file, to our programming and proof development, right? So now I kind of have an interesting way to change my specification. Maybe you've guessed it already, which is to say instead of saying that, yeah, the tree is the empty node, right? I'm giving too much details about implementation. So let's say that the size of the input tree T is equal to 0, right? So this is a much more declarative, if you want, some specification, right? Okay, so let's get back to Y3 to see if this is a good specification, or I mean, is the empty tree function meeting this specification? So Control R once again, and now, yeah, I have still 2 post conditions. Let me try 0. Okay, so it seems that CVC4 is not particularly happy with the fact that I have for the second post condition, I guess. Yes, in the case that this is a false one. Okay, let me see if I need to do a split once again. Yeah, that's the case. Yeah. So what I see is that there is still a couple of, I can still split this one. So then, because it can be done in 2 separate steps. Okay. Yeah, maybe not. I mean, it's not provable at the point. So let me see if I can do a new step. Yeah, here. All right, let me check. Yeah. Okay, so this is an interesting one. Okay, let me see why this was supposed to be okay. Let me just wonder if I need a little bit more of specification at this point. Okay, I don't think I should be needing this one. Yeah, this is the live demo effect. So let me do alter go a little bit more time, because otherwise I'll try to. Yeah. Okay. So that's not important. I know how I can fix this. Okay. So now that we have the size tree function, I can, as you can see, I could write some very, very interesting specification, but now I'm not able to use it or to prove it. And the reason is that I still need, or I want to prove properties about this logical definition. And so at this point, what I can do is that I can write a lemma that states that both size tree and size forest, both of them return always non-negative values. Okay? And so let me try to write this as a lemma. Okay, a logical lemma. So what I can say is that I could write something like size tree non-neg, sorry, and I could do something like for all t size tree t is always non-negative, right? And I could do the same thing for size forest, right? So for any forest, size forest is always non-negative. So if I get back here, let me see if these lemmas would help. Yeah, sorry, he's telling me to this is polymorphic one, so I need to quantify because it doesn't know where it's going to be used. Yeah, size for, oh, sorry, my bad. So this is a forest. All right, so does this help the post condition? Yes. Okay. So actually, by providing these 2 lemmas, now I know that it is indeed the case that even when the tree is the non-empty tree, right? Its size, if I do another split thing here, yeah. So this one, the size tree here t equal to 0. So now I know that this is an incoherence, right? So there is no way I could have a size of tree of t to be equal to 0. Why? Because I know by definition, I can go back here, that this is equal to 1 plus the size of the forest, okay? And actually, this forest here, W, never returns a non-negative element. So even if it runs 0, size of tree would be 1, so this is an incoherence. So I could prove anything, in particular that b equals to true. So yeah, these two lemmas help me. Now, what I need to do is, I need to try to prove the lemmas. All right, so let's begin with the second one, maybe. Let's try with the second one. So I'm pressing 0. No luck at all. All right, let me go with the first one. I'm also pressing 0. No luck at all. Okay, so I'm starting to get a little bit worried at this point. Okay, so is there any problem on my specification? The lemma is not good, because if I wrote a lemma that is not that is false, it's up to no good use, right? So it doesn't. I can no longer rely on such a lemma to finish my proof afterwards, right? So, but maybe by looking into how t is defined, right, and how size tree is defined, maybe I can guess that this needs a proof by induction, right? So the first thing, let me do a split here, right, just to show you the difference of the task. Split implicitly also introduce some premises. In particular, it will introduce the variable t into my context. Okay, so now I can use Y3, the very interesting part where you can do some lightweight proofs, some lightweight interactive proofs directly on Y3. For instance, I can call induction arg tilex, which is going to do induction over a lexicographic defined data type, and arg is to say that I'm specifying my argument as t. Okay, and so what it's producing is that it has produced two goals. Okay, one is that is the base cases, and right, the one where the tree is empty, and the second one is where the tree is not empty. So one where you need to apply your induction hypothesis. So let me split. Okay, let me do a 0. Okay, so the first one is very easy, but the second one, not so much, all right? Well, and that actually is the fact that you need to write, or you need to rely on size forest when doing the inductive step, right? So in some sense, you need to state before proving size tree non-neg that size forest non-neg comes before. Right, so yeah, let's try to do that. Does that work? I mean, I'm going to change slightly the order of the two lemmas. Right, so I'm doing the Control R here. Okay, so let me see if I get back to the proofs where I were. So is empty is still good. Let me clean this up here. So now, is the proof done? Yeah, so the proof of size tree non-neg is okay, right? So in particular, you can see that I have a very, very interesting hypothesis on my context, one that readily applies in my case. So now the things that I could do would be to try to prove this lemma here about size forest. So the forest is a list. I have some hope of doing this by induction, right? So I split. I get f on my context. So let me do the same trick again. Induction arg tilex. Now f, two cases. One, the empty list, for the empty list. The second one, when the list is not empty or the forest is not empty. I split, right? And so yeah, let me see what I can do here. All right, so let me do a 0. Yeah, and so once again, so this is the inductive step, the step where I wanted to, or the case where I wanted to prove that a cons forest, or the size of this forest is always non-negative, is not provable by any SMT, right? And the fact is that since size tree and size forest are mutual recursive functions. So then the two lemmas should be also stated and proved also in mutually recursively. So it's up to no good use to try to do them separately as two lemmas. So let me clean this up. And now what I'm going to do is that I'm going to introduce a lemma as an OCaml function, and this is normally called a lemma function, right? So this is actually very, very, very interesting because now I'm actually doing my proof by induction directly as an OCaml program. I really find this very, very interesting. So a lemma function, in Cameleer, you attach the attribute lemma in order to say that this is a lemma, right? This function should be a particular one, should be treated as a lemma. And lemma functions take a bunch of arguments, right? In this case, it's going only to take a tree as an argument. And all the arguments of such a lemma are implicitly universally quantified, right? So, which means that for every tree T, if it's the empty tree, so there's nothing to prove. Okay, so I use the unit value, right? Because lemma functions are such functions that always return unit, right? And now, but sorry, when is the case that not the empty, it is not the empty, how to say that? It's not the empty tree. So now what I need to do is that I would need to call another lemma, right? One that says that, okay, forest non-neg. I'll define it in a couple of seconds. So right now you've guessed that, yeah. So this is the point where I define the second lemma recursively. Okay. Now for size forest non-neg, I'm actually doing something very, very similar. Well, if it's the empty forest, nothing to prove, right? And if it's not the empty forest, okay? So in order to be able to finish my proof, what I need to do is, first of all, I'll call the tree, or the lemma that talks about the tree, right, on the first element of the forest, right? The tree one, the T1, sorry. And so this is actually a call to the first lemma that I've defined here. And now what I do is that I use a semicolon, and what I can do is now to recursively call the exact same lemma that I'm defining, size forest non-neg. Okay, R, right? So now, these are not, how to say, very interesting lemmas if I do not say anything about them at all. So for instance, what I need to do now is that I'm also going to provide specification to these lemmas, okay? So what I'm saying is that this function here, size 3 non-neg, it terminates, of course, because otherwise it's not a valid logical definition. And as an insurance clause, okay, so size 3, all right, what this lemma ensures me is that every time I call size 3 function over T, okay, remember that T is implicitly universally quantified, right? It always returns a non-negative value, sorry. And I can do a very, very similar, or provide a very similar specification for the second one. Also, this must terminates, right? Sorry, I'm calling this F. And the post condition is actually very, very similar. So, but in this case, I'm going to call size forest, right? Okay. So I provided a specification to a program, to a OCaml program, but it happens that this program is a lemma function. And so in practical terms, what it means is that this function here, its specification, is going to be turned into a statement to be used afterwards, like you have written lemma in the first place. So let's get back to Y3, Control R. All right, let me do a clean here to erase these old nodes. All right, so let me see if is empty tree still is the proof is still doable. R, okay, so everything is okay. So now what I see is that I have these two functions. Okay, this is our at this point these are regular functions, right? That I need to prove the specification. But I can take a look at this empty tree, in particular the task, and now you can see these two statements, right? So what happens is that these post conditions here were automatically translated into axioms for your proof context that you can use, right? So you see that now the tree and the forest are actually universally quantified. So let me do a 0 here now that I got back to the size3 non-neg function, or to the size3 non-neg lemma function. And yeah, the post condition does not go through. It goes through after a while, or AlterGo is able to prove it. So it's an interesting case where CVC4, neither CVC4 or Z3 are able to do it, but somehow AlterGo, or for some technical reason, AlterGo is able to do it. So I'm pretty happy at this point that Y3 allows me to interface with many different SMT solvers. I'll do the same for the other lemma. Okay, the post condition is also hard, but not so much for AlterGo, right? And so at this point, I have everything I wanted, and it's proven, or my lemma function is now proven. Okay, so let's now use this size3 logical definition in order to complete the specification of singleton and add 3 functions. For the first one, let me name the result R. Okay, so it takes X as an argument. And so what I can say is that, yeah, is resulting tree, its size, right, is 1. Yeah, it's a tree that contains only one element, no descendants. So getting back to Y3, Control R once again. So now singleton is asking me to show a post condition, to prove a post condition. Okay, yeah. In this case, that is somehow, is inlining the proof code inside the post condition itself. So let me try to do a 0 here, and CVC4 almost instantaneously does the job, right? And so now I can also use this one, or this specification also, for add 3, right? So the first argument, I'll name it X, the second one I'll name it T. And so what I can say is that the size of the result 3 is actually 1 plus the size of 3 that was my initial argument. Getting back to Y3 once again, this is a very incremental process, right? All right, so for that 3, is this also doable? Let me do a split just to see the 2 post conditions, yeah, for both cases. And now I do a 0 here, and CVC4 does the job. And now the fact is, I come up with a point where I'm happy with my code. Everything is green, so I'm also happy with my specification. That I'm pretty happy now that the implementation meets the specification that I just built. Okay, and I can say, yeah, my code is sound here. Here it is a bulletproof implementation of a couple of functions that deal with trees and forests. Well, how about being sub-specified? Because let's take a look back at singleton tree, right? Here I say that, yeah, the new tree only contains one node, but does it contain the X node? I mean, I'm actually stating everything that I need about this function. So let's do a simple exercise, all right? So instead of putting X here, I'm putting 0, right? So this is okay because now, instead of having a polymorphic function, I can use Merlin to tell me that now this is returning a tree of integers, okay? So getting back to Y3, Okay, so let me just do the proof of add tree once again, because this is not the case. This is not our focus anymore. So now about singleton tree. So does this post condition still holds? Right. So let me call 0 once again, and yes, right? So what I see is that I do not have a strong enough specification for this function, right? Because one better specification would be to, yes, the size of a tree is 1, but what happens about the occurrences of x inside the new tree? So I get back here to the top of my my file, and maybe what I want also to do is to write the logical definition of the number of occurrences of an element inside the tree. Okay, so let me do this as a logic function. Okay, so what I'm telling you, this is of course a recursive definition. So at this point, I need to put some type annotations, because otherwise y3 would be angry with me. That's not a big issue. So I'm matching on top of t. So if it's the empty tree, there is no such occurrence of such an element x, so 0 occurrences, right? So otherwise, if it's a tree with an element y, right? What I needed to do is to do something like, for instance, if x is equal to y, then 1, else 0. And now, what do we need to do is actually rely on a new um, function that I have not yet defined to compute the number of occurrences of x inside the forest L. So let me do that right away. This is a logic one. Okay. All right. So if it's the empty list, yeah, you guess there is no such occurrences. If it's a forest with t on the head, what I need to compute is the number of occurrences of x inside t plus the occurrences of t inside the remaining forest R, right? So yeah, since these are logical functions, let me prove that they are terminating. The parent is actually always structural at these kind of cases. And here, awk forest takes f, s, and f. Yeah. All right. So now let's get back to y3 before actually using the definition of occurrences to provide specification to the other functions. Right. So let me do a control R. And yeah, I have here a nasty typing error, which says that this expression x has type alpha, but it's expected to have type int. Why does this happen? Well, in Y3, there is no such thing as a polymorphic equality, okay? Because it's unsound to support such thing in the presence of ghost code. And I'm also following the same approach here in Cameleer at the moment. As future work, I'll try to provide some form of polymorphic function or polymorphic equality, sorry, out of the box. But for the moment, equality, this symbol here is only usable for integers, right? So you can only compare directly integer x and integer y, which is not the case because we know that this is of type alpha. So, but still, this is a logical definition, right? So I'm not using this as a program function. So it should be okay to try to abuse things a little bit and still rely on a logical polymorphic equality, right? And yes, I can do that in Cameleer. So let me just run this expression by parentheses. And what I'm saying is that please consider this equality as a pure computation, okay? And so now, let me get back to Y3, do a control R, and now he's telling me a different error, which says that function awk3 must be explicitly marked the ghost, which is okay for my purpose because I'm only going to use this awk3 for specification. So I don't mind attaching a ghost attribute to both of them. Okay, so this is the way that Y3 is helping me to build things properly in order not to mix ghost and regular code, or since I want to be really sure that I want to use a polymorphic equality, it's only usable inside purely logical definitions and ones that I have no right to use inside the code. That's why I need to mark it here as a ghost function. Getting back to Y3, now Control R, and now it is not complaining. It says that it was successful. Okay, redoing the proofs that I had done before. Okay, so now I have two awk tree and awk forest verification conditions, which just state that these are terminating functions. So now I'm going to directly do 0 here, even before doing a split, because these are easy ones. No need for a split. Let's see about awk forest, and neither awk forest needs a another one. Okay. All right. So now, what I need is to be able to use these awk forest and awk tree inside the specification part. Okay, so now I can really write some very interesting specification, right? And for instance, I can go back here and write, for instance, that awk tree of x inside the result is actually 1. Okay, so yeah, let me do this. Second, yeah, sorry, yeah, I think I'm done. I think I missed the value of the arguments. No, it should be done. Okay, what's this error? Yeah, but it's expected to have. Yeah, so I need to help him a little bit here, I guess. No. So why he's complaining about the types? Oh yeah, sorry. Now I need to get back to put x here. Yeah, he's right. Okay, so now, okay, let me just do head 3. Now the new post condition I'll do 0. All right, and so this is provable. Okay, sorry. So yeah, now I know that I have a much more complete specification, but I can still do a thing like for every other one. Sorry. For every other element in my domain that is not x, so its occurrence inside the tree is equal to 0, right? Okay, so let me do this, a control R here, do a 0, and yes, it's also provable, and here it's also provable. That tree has not changed. So let me do a nicer specification for also the add3 Okay, so now what I can say is that actually, as I've done before, the occurrences, let me copy this one here. Okay, the occurrences of x in the resulting tree is 1 plus the occurrences of x in the previous tree, because it could be elements that were also equal to x, right? Now, what I can also do is to say what happens to every other element that is not equal to my x, right? So it says that then in the resulting tree they have exactly the same occurrences as before. Okay. All right. So yeah, the xt y3, and so let me put right up here to a 0 on the head. Yeah. Okay, so he's having a hard time doing this. Yeah, let me do a split, try to help him a little bit further. Yes, so after a split, he's able to prove it, because if you take a look at the task, there is still a big pattern matching, and so when I split, I have no pattern matching whatsoever, so it's easier for SMT solvers. Right, I'm doing some case analysis on top of my proof. Okay, yeah. So now, the last thing that I want to show you in this example, I'll put a more complete version of such an example on the GitHub repository, right, with other interesting functions. So let's now imagine that I want to have a type T, okay, that not only contains a tree, let's call it root, but one that helps me to compute in constant time the size of a tree. So it's here I put it as a field, right, of the type itself. And so what I want here is to attach this type invariant to my newly defined data type. Okay, and this one says that in particular, the size field is always the value, or this has the same value as calling size, the logical definition of size tree to the root field. Okay, so now if I get back to Y3, I do a reload, and I see that I have a condition to verify regarding this type invariant. And what does it say is that I need to prove that there is at least one inhabitant of such a type that respects this type invariant. So not to be introducing some false type invariant in my context. So this is actually very easy for TVC4 because it's able to understand that the empty tree would and the zero value for size would satisfy the type invariant. Okay, so now that I have this type, what I do is that I can write a bunch of functions that are now building this type on top of a tree. And for instance, now I'm doing the empty function, and I'm doing the size equal to 0. And so what the type invariant really gives me is the fact that if I do a control R, I automatically have a generated verification condition because I'm building a new value of a type that has an invariant, right? And so automatically Y3 is telling me that I need to prove that the size of the tree, the new tree, should be equal to 0. And yes, that is the case. Okay, so TVC4 was able to do it. All right, so now let's write a singleton. Okay, let's write a singleton function, one where I'm putting on the root what? Yeah, I can call singleton tree here. I have done that function, why not to call it here? And so size is equal to 1, right? And so the same thing will apply on the proof side. I do a control R, and once again, there is this nice verification condition without ever stating any sort of specification. I split, I have a precondition, and this precondition here is the way that Y3 is referring to the data type invariant. And this is also doable after pressing 0 by TVC4. Finally, the last function that I want to show you is the add one, right? So in this case, yeah, the specification, I don't have any specification at all, right? So the thing that I'm doing here is I'm only calling add tree to the root, and size will be 1 plus what? T.size, right? Okay. So back to Y3, new verification condition, also precondition, so it's referring to the type invariant, right? So 0, TVC4, and maybe alterable. Yeah, alterable is also able to discharge this very simple condition. Okay, so I could even try to more simply write this one, right? Like this. This is also supported by Cameleer. So at this point, I would simply do this. I've done a reload. Let me try to do this. Yeah, and so the proof is also doable. Yeah, so I'm running a little bit short on time. Yeah, I was a little bit ambitious to try to show you 4 examples, but no worries. I'll upload every single example with the instructions to the GitHub repository. And actually, I'm also putting on this example delete function. Okay, adding this delete function to this example. Okay, so let's go directly to the second one. Second example. Okay, and so this is a very, very simple example. It's just an excuse for me to write a loop invariant. So I'm trying to find an element X inside my array A, okay? And so the way I'm doing this is that I'm declaring a local exception found, and whenever during my traversal I find the element array is found, and it just returns true if the element is found, false otherwise. Okay, so in terms of specification, let's begin by the post condition. So what I can do here is that I can say that, yeah, as a post condition, it returns true if and only if what? If B, sorry, I don't want to do this by right now, yeah. If B, then it is the case that there exists an I within the limits of the array. Okay, and such an element is equal to the one that I'm looking for. Otherwise, for all I that is within limits of the array, then there is no such element that is equal to X. Okay, so let me call Cameleer on this second exercise. Yes, I'll drop the section that I was looking for. Oh, sorry, yeah, I made a mistake, but Cameleer and Y3 are really my friends here, because I'm not supposed to write this on an existence show quantification. It's sure is right. So what I want to do is to actually write this as an AND clause. So yeah, let me call Cameleer once again. And so now, once I do a split, I have a bunch of conditions that I need to prove. Okay, let me do a 0 here. So at least this program is safe, yeah, in the sense that every access to the arrays is done within bounds. So there is no index out of bounds access, right? Which is cool because I'm inside a for loop, so that is already guaranteed. But there is a post condition that is not verified. It's the one where I'm saying false, right? And it comes with no surprise that I need a loop invariant, right? So I'm doing it here. So I'm saying that, yeah, for my loop invariant, what I want to say is that for every element that I have already scanned, right? So for every j that is strictly smaller than I, then A of j is different than X. Okay? And so with this loop invariant in hand, let me do a control R here. But now I need to prove things about the loop invariant itself that is true before the first iteration. This one will still done. Now I need to prove that it maintains after each iteration. So it's a loop invariant preservation. So I do a 0. CVC4 is pretty much okay. Right? This post condition was already proved. So let me do a 0 once again. Remains provable. And this one was the one that I was not able to prove before. So now with this type invariant, with this loop invariant, should I be able to do it? Yeah, so let me try to do a split before. Yeah, so I have two post conditions here. And I'm pretty hopeful that with this loop invariant in hand, I'll be able to do it. So let's press 0. No? Yeah, AlterGo is my friend, and yes, he's able to prove it. Okay. So now, let me change the code slightly a little bit. All right, because, yeah, these functions just say true or false whether the element is there, but it's not very interesting as a function, but it should return the index where the element is found whenever that's the case. So let me change my exception here, right? So instead of just found, I'll say found of I, right? So, and now what I can do is, for instance, to do this. When there is such an element, I return sum of I. When there is no such element, I return a none. Okay? Now it comes with no surprise that I need to change my specification because my B is not a Boolean anymore. So let me change it to a different name. So now what I need to do is kind of a sort of case analysis on the top of my result. So I can do a match inside gospel terms, which is very nice. So if it's none, Now I'm taking back some of the old specification elements, right? So I'm saying that if there is none, so there is no such element within bounds that is equal to x. On the contrary, and now this is much, much more interesting. Now I have a witness where the element is found. Okay? So now I say that the return I rubbed on the sum constructor is the index where x was or can be found. Okay? Let's go back to y3, do a control R here. Yeah, the specification changed a little bit. So let me do a 0 to see if things are still okay. And things are still okay, even for the more difficult post-condition alter go is able to do it. Let me see if somebody else is able to do it without a split. Not C4, not C3, but alter go, yeah. So I don't even need to split it here at this point. Okay, so this is just an excuse to show you the way to write an invariant for a loop invariant in Caml. Okay, so now this example I'm not going to show you in many details. This is the queue implementation. So I'm uploading these, and you can look after the tutorial. But I invite you also to take a look into last year's ML workshop keynote by Arthur Charguereau, where he also proved this very same implementation using the CFML tool, right? So here, what we can do in Cameleer is that you can build the data structure and build a function like Inplace Concat, one that is going to empty Q1 and pushing elements to Q2, right? In a fully automatically way, which is not the case with CFML. Okay. So once again, I promise I'll upload this example, and I'll put with many instructions on how you can reload it and replay it on your site. So the final example that I really want to show you is one about leftist heaps. Okay, and so this implementation is exactly the one that I took, or is exactly the one that is presented in the OCaml containers library. No change to the code, whatever. Right, so leftist heaps, as described by Okazaki, are heap-ordered binary trees that satisfy the leftist property. What is such property? Well, the rank of any left child is at least as large as the rank of its right sibling. So, in other words, the rank of its left child is greater or equal to the rank of its right sibling. And the rank of a node is defined as the length of its right spine, or the length of the rightmost path from a node, from that node to an empty one. A very nice consequence is that on the leftist heap, the rightmost path, or the right spine, is always the shortest path until you get to an empty node. Okay, so as presented in OCaml container library, the module type pre-order, it just said in natural language that this is a pre-order relation, right? And what I need to do is that in terms of gospel specification, okay, I took the following approach. So I say that there is a predicate called LE, right, which takes two arguments of type T, and this predicate satisfies the three expected axioms: reflexivity, totality, and transitivity. Okay, and so now for the actual LUQ function, what I'm actually saying is that it always returns the same value as the predicate that I have just declared, the predicate LE, right? And so now the S module type is the type of the functor, right? So now I also need to put here the definition or the declaration for this logical predicate with the very same axioms, and everything will come in good terms when I'm going to instantiate the function and do these refinement proofs, as in the demo of the first part of the tutorial. Okay, and so I need this LU relation in order to write my specification for the signature itself. So for the signature, I have a data type T, which represents the heap, the lefty's heap, and I have a bunch of functions. For instance, size, which is also a logical function, right? To be used as the size of the function. Since this is an interface, I'm not giving too many details here. I'm only saying that the size function always returns a non-negative element, right? So this is my way of implicitly writing a lemma function that we wrote in the first example, okay? So here I can directly do that inside the function specification. So since this is a heap, I'm going to model it as a multi-set or a bag. So I'm going to use a function occurrence, right, to talk about the number of times some element can be found inside the heap. But everything here, since this is an interface or a signature module type, I'm only going to declare what does it mean. I mean, I'm just going to say, yeah, trust me, there is such thing. These things will be instantiated in a minute, that there is an occurrence definition for my elements inside an heap data structure. What it means for an element to belong to the heap, and very much important, what is the minimum element of the tree, right? So I'm defining here a function that returns such minimum element inside specification. So since this is a function, this is a total function, so it's always going to return the very same element when given the same argument, okay? So, but I also need to define what is logically, or what is the relation that a minimum element must respect. And why? Because let's think about it for a while. There is nothing that forbids you to repeat some element inside an heap. But the minimum element of the heap is very well defining in physical terms, because it's the root of the heap, right? So imagine that you have a heap of integer values. The root is 42, so that's the minimum element according to the LUQ criteria that you're going to give to your functor argument, right? But let's imagine that somehow inside the heap there is another node with 42. That's not the minimum element. So you need to be very careful when working with heaps to precisely state that the minimum element is the top or the root of your heap. Okay, so you say that as an axiom that the element that respects the is minimum property is an element of the heap, and for everybody else that belongs to the heap, those everybody else elements should be should be greater or equal to x, right? X can be equal to somebody else, right? But no greater. And finally, what it means to be a heap. Okay, this is a predicate that I'll be instantiating in a moment, but now I can define it as saying that if I have a well-formed heap, right, and this is a non-empty heap, then I can retrieve the minimum element, right? And so it is such an element, and this one actually is respecting this minimum element. This seems like a redundant definition, but I assure you that it's not. We will see in a couple of minutes how everything works in practice for the implementation, right? And so now finally, I'm just declaring what it means for a heap to be left is heap, and I can begin to define my functions, right? Empty, all right, is empty, and now you can see that for every function that takes an argument of type t, I need to be careful enough to provide a precondition that states that such an element is a well-formed left is heap, right? The merge functions, both arguments are left is heaps, and as both conditions, the resulting one is still a left is heap. And more arithmetic conditions, like for instance, the number of occurrences of an element on the resulting tree is actually the sum of the occurrences on both argument heaps, right? And the size is also the sum of the size. The insert function, which also follows the same approach as in before, And the filter function is actually our first example of a higher order function, right? Because it takes as an argument the p predicate, right? And what I say is that by the end of the function filter, everyone that does not respect this predicate p should not remain in the heap. Everybody else should remain in the heap. Okay. Now, two variants of the find mean. One that is using how to say that is returning an option type when the heap is empty, and the other one which is raising an exception when the tree is empty, right? So this is kind of a big filter function that deletes all the elements that respects some predicate. Okay, so now I get to the implementation part. So a leftist heap is built or is defined as a binary heap, a binary tree, sorry, with the first element, the rank. Okay, so I could also be doing this as using embedded records in my algebraic constructor, which is supported by Cameleer. But I'm not doing that because I really want to stick with the actual implementation shown in containers, which is this one. So now I can define what it means for logically the rank of a tree, and so we call that this is the minimum path until you get to an empty node. So yeah, it's actually almost the dual of the height of a tree. It's because I'm doing here the minimum instead of a max. And now I have everything I need to be able to say what it means for a tree to be leftist. Okay. And so an heap is leftist if the n here is always storing the rank, the right and left subtrees are also leftist, and the rank of L is always greater or equal to the rank of R. Right? This is the leftist property. This is the most important property about this heap implementation, right? And so for the remaining of the file, I have size here, which is already specified. Here, I do not really mind to do this post condition because my client is only going to see the size of an interface where I do not give much details. Okay, so he doesn't even know that there is such a thing as a E constructor. And now what I'm going to do is that in logical terms, I'm giving definition for every logical symbol. So here is the occurrences part, lemmas about occurrences, right? Membership is just to have a positive occurrence, right? And now I need to define what is actually the heap property, okay? And this is the fact that the root is always the minimum element of the tree. So I define via this predicate LE root, all right? And I write a very important lemma that says that, well, if x is smaller or equal to y, and y would be a valid root for my heap, then x is also a valid root for my heap. And so this is how I get to the heap, this heap property. So the root is always the minimum element, and the left subtree is a heap. The right tree is a heap, all right? And also x is a root, or x as a root for the right subtree. And finally, the last pieces of specification for this for the heap data structure is actually the minimum function. And now I can give one single axiom to a definitional axiom to it, is that minimum is only defined in the case where this is the non-empty heap, right? And the predicate is minimum now as a very straightforward definition, right? Membership, and that every other element, for every other element x is less or equal to that or every other element. And now the very, very important lemma is stating that in this state as a lemma function. Okay, so if my parameter is a heap and it's a non-empty heap, then the minimum function here, the axiomatized function, is actually returning an element that respects this predicate here. And finally, a leftist heap is a heap, and a heap that respects the leftist property. Okay, so now for the remaining of the functions, okay, in the minutes that I have left. So you can see there is not so much specification attached. So let me see what happens if I call Cameleer on this example. So it's called X for example. All right. So you see that there is all of these big refinement proof that I need to make, which means that all of these functions should refine the specification, in particular, should refine the specification that I gave in the first place in my signature module type S. But the thing is that I have not given many specification details to the programming functions on the implementation side, right? So let's maybe go to the easy one. Yeah, let me see if I have an isEmpty function here. I guess I do. Yeah, the isEmpty function, right? Yeah, maybe with empty first, because I'm not sure if I have an empty one here. I have an empty one here. Let me see if this is provable. This is actually provable because it's a logical function. So Y3 is able to inline it, and I've defined it here. And so constants are always logical definitions. But I can also attach a post condition to it just to say that, yeah, in this case, since this is the implementation, I'm not showing this to my client. It's okay to do like this. All right. So it's still provable. And on the refinement part, and the actual implementation is also provable. All right, so isEmpty. Do we have isEmpty? Yes, we do. Let me see if I can do something about isEmpty. In this case, no. So this implementation here, for the moment, does not refine the isEmpty implementation here. Right? Why? Because of the preconditions and the postconditions. Now getting back to the actual implementation part, what I can do is that, sorry, if I now attach the expected, I call it this H, the expected specification, right? So I need to say that, all right, so this is true if and only if the parameter is false. Is the empty if, but also I need to say that, of course, this should be only applied to leftist heaps. That's the whole purpose of this development, right? So getting back to Y3, now I do a Control R here. Sorry, no parameter. No, it's called H. Yeah. So empty is still doable. Now the isEmpty part, the new specification on the implementation side. Once again, yes, that's provable by CVC4. Now the refinement part, which is not proved before. Now it is. Okay, so I'm incrementally doing more specification in order to be able to close the gap between the signature and the actual implementation. Okay, so for instance, the rank function. Okay, so you guess by now that these, now I'm calling param. Why not? Just to change. Once again, this should be only applied to leftist heaps. And I think you've guessed that this is only an implementation of the logical rank function. Right? So I can keep going with the make node, which already has a more interesting specification, because I'm building a new leftist heap here, right? So let me call this the returning value H, right? So the precondition, what I just want to say is that both A and B are leftist heaps, right? Now, very much important, the X argument should be a valid new root for the heap, okay, and also for the heap B. Yeah. Now gets to the point of the post conditions. At this point, I say that yes, the result must be also a leftist heap, and the new minimum of the new heap is the X argument, right? And so now I can go back to my more arithmetic arguments reasoning, right? So the size is incremented by 1. Sorry. And also the occurrences, right, of X are incremented with respect to how much times X occurred inside both heaps A and B. All right. So now, for everybody else that is not X, its occurrences are exactly the same as it were before. Sorry. Okay. Does this specification, or I mean, the implementation of make node meets the specification? Let's go back to I3, Control R. So now, yes, rank node. I also had some specification. Well, let me do a split here and press 0, and everything is proved for make node. So do I have a make node? No, there is no such make node on my interface, on my signature, because it should not be exported to the client. It's an internal function. More interesting, I can now provide specification to the merge function. Okay, so I've already provided the variant. Okay, but now the precondition, I think you have already guessed by now. So yeah, I've called T1 and T2. So both of them must respect the left is heap property, right? And that's the only precondition I need. So the size of the new heap should be exactly the sum of both sizes, as it was already stated in the module type S, right? And in terms of occurrences, okay, for every element, let's call them X, its occurrences inside the new heap should be exactly as before, okay? Or the sum of both the occurrences on T1 and T2. Of course, I still want to have a lefty heap as my result. Okay? So before doing a reload, right, was I able to do the refinement of merge here? With no surprise, I was not. Okay, no post condition was able to be proved. So now I do a Control R in order to bring up a new specification for merge. I'll do the refinement part in a minute. So let me do a split here. Okay, so now I call 0 on this specification. Let me see what happens. Okay, SMT solvers are still running. So now, yeah, some preconditions are not proved. Let me see. Can I do once more of a split? Yes. So now is it good for you? Let's hope for yes. AlterGo is able to discharge it. So AlterGo is my friend. And now you can see that in the post condition, right? The post condition that the size is the sum of the sizes of the input arguments. Okay. This has a huge pattern matching as a formula, as an hypothesis. So let's do a split to help SMT solvers. Now I've done a split. Let's press 0 once again. And now they are very happy with me. They are able to discharge. The same thing goes by for post condition 9, with no surprise for post condition 10, because the hypotheses are always the same. And now, yeah, the merge function is proved. What about refinement? So now this specification is good for refinement. Let's use the split I've done before. And yes, now the specification, because it's exactly the very, very similar one. Let me do a trick here. Let's look into this merge specification, and let me go by here. And yes, you can say that it is almost exactly, or it is exactly the same specification as before. So yeah, it comes as no surprise that this is provable. Okay, so I'm really finishing here. So you can guess that we could go on and add more specification to the elements inside the implementation part. All right, so that will allow us to finish the proof of the refinement part. So let me show you what it looks like. The example in full. So now you can see that I have the very same OCaml development. Okay, and now I have everything, every single function annotated with proper gospel specification. Okay, most of the time this is exactly the same specification as in the signature S, but sometimes it can be different. The important part is that the implementation specification is included in the specification of the interface. Okay, so yeah. I actually added a bunch of other functions like delete one and the delete all function. So now if I call Cameleer on my left heap development, there are some warnings, and now you can see that actually everything is proved. So the refinement part is, which is for me the most interesting part here in this development, is proved. Okay, together with the actual implementation of each function. And this only happens for Cameleer because I have here said that this is S with type element instantiated with the type T from the argument function. And also gospel allows you to write that you instantiate S, where the predicate that I have put here on top of S, let me go back to it. Yes, this one is instantiated with with the one that comes from the functor argument. So in particular, you need to prove the axioms. Let me see if they are here. Yeah. So you need to prove that these axioms reflexivity, totality, and transitivity. And this is only due because I've told Cameleer that these S module types should be constrained to using the Ali instantiated with the one that comes from the functor argument. So if I do none of this, and I just go ahead and do the module without no type constraint, so I rerun Cameleer. So now you can see that I only have that these were just historical notes. I can delete them. Now you can see that I have only the implementation part that I need to take care of, right? So at this point, there is no need to conduct any refinement proof. So let me get back to the state that I was before, because I really like this refinement proof. Let me see if everything is okay. Yeah, so let me do a refinement proof as before. And the refinement is actually very, very simple because the tasks are very, very much easy. So it's a very, very simple tasks. And most of the times, in particular for function definitions, these are the same specification. And even, for instance, this is minimum def, which you can, if you recall well, it was this axiom, right, in the signature. So now, when I get to to the actual implementation, now I have an actual definition to give to my predicate, and so I need to prove this axiom is now valid. The same thing goes by for the minimum def axiom. So this is quite reassuring, is that even if you introduce some axioms on your specification, because at this point in the interface you can only write axiomatic stuff, Cameleer will generate enough verification conditions using Y3, of course, so you to be sure that your axioms are actually valid axioms. All right, so I guess that's it. Yeah, that's it from my side. I'm really sorry that I had to speed up a little bit, but once again, I promise that I'll put everything online and I'll actually identify them as the exercises of the ICFP tutorial. In particular, the ephemeral data structures are interesting, since I have a couple minutes left, just to show you what it looks like. So you can see that in particular, I have attached the ghost model view to my implementation, and now my specification is always written in terms of this module view, right? So in particular, I call it tree transferred, but you can replace this by Inplace Concat. So you can see that actually I'm telling you that there is no such thing as not found exception raised by this function because it is protected by this one. So this transfer function is safe. And I've emptied the Q1 view model, and I've attached the elements of old Q1 to the elements Q1 view to the old elements of Q2 view. The invariant property is actually, the loop invariant is more and more difficult, but after some while you see that this is actually, this part here, this big part, you are only reproducing the type invariant that I've put here for my ephemeral data structure definition, right? So actually Y3 asks you to do this. Yeah, he's not able to infer it by itself, right? But after a while you understand it's just a copy paste to retell the type invariant for both Q1 and Q2. And right, and the actual interesting part is this one, which is a very, very simple property, which says that at any point during the iteration, the elements of Q2, the concatenation of the elements of Q2 plus the elements of Q1 is exactly the same thing that if you had attached directly in a single step the elements from old Q1 to the elements of old Q2, but now you are doing it step by step using a loop and stating that as a loop invariant property. Okay, time to see if I have any questions in the chat. I do not see any, so I'll stop my sharing my screen here, and I think we can still have time for a couple of questions if you have some. So I'll gladly take your questions at this point. And thank you very much for your attention and your patience to be in this tutorial. It was really my pleasure to be here with you today. All right, so I do not see any questions. Yeah, I think it's lunchtime for everybody around Europe, at least. Yeah, so maybe 10 seconds more to see. People are already leaving the session. Yeah, so if you have the opportunity, let me do a little bit of announcement here. If you have the opportunity, please take a look into our ML and OCaml workshops presentation. In particular, the OCaml one is the one where Carlos Pinto, my student, will be presenting the verification of a module from the OCaml standard library, in particular the set module. So a realistic OCaml code, and one that is of course widely used since it's shipped with the standard library. Okay, so yeah, I think that's pretty much it. Once again, I really would like to thank you all for being here today with me. It was my pleasure to deliver this tutorial. It was really fun to do these live demos of Cameleer, and I hope that if you get interested, please send me an email, and hopefully you get to use Cameleer in the future. And if you have any questions or about Cameleer itself, or any problem or a bug in the tool that you need me to patch, please feel free to send me an email or to open issue on the GitHub link. Okay, yeah, I think I can do that. Actually, that's a good idea to finish up by providing you with the GitHub link on the chat. Yeah. So that's pretty much it. Thank you once again, and see you around at ICFP. Bye-bye. Thank you.